Hey, so this next video is on power series. It's talking about the differentiation and integration of said power series. So in class at length we've talked about the specific power series. It's 1 over 1 minus x is equal to the sum of x to the n from 0 to infinity. So if I write out the terms, then if I expand the sum a little bit, it looks like x to the 0 plus x to the 1 plus x to the 2, etc. And of course, just for you to know, it looks like 1 plus x squared plus x cubed plus all the way to x to the getting bigger and bigger and bigger. So this converges as long as the absolute value of x is less than 1. So remember, x has to be between -1 to 1 for this to converge. Right, so we want to, let's say, find a power series representation for a function like ln of 3 plus x. So an example, this is an example of where we can use integration and differentiation in order to get a power series for this. So 1 over 1 minus x has a power series representation of this, right? Or this, doesn't matter how you write it, they're the same thing. Let's see if we can find one for ln of 3 plus x. So the key here is trying to find an expression through either integration or differentiation that will look very similar to this. So I'm going to walk you through the example how to do this. If I take the derivative of ln of 3 plus x, then I'm just going to get back 1 over 3 plus x. Right, just me taking the derivative, that's what it is. 1 over 3 plus x looks a lot like this, right? The 1 on the top is the same. This 1 here is actually a 3 over here, and the plus is the minus. Anyway, so let's try to rewrite 1 over 3 plus x kind of in this form, right? So that I have 1 here over 1 minus something. This something can be different. It doesn't have to be specifically x, but the rest of it has to be the same form. So 1 over 3 plus x, well, I have a 3 here, but I want a 1. So I can factor out a third, and I get 1 over 1 plus x over 3. Well, we got a 1 here now. It's almost there. This minus, this is a plus, so we get 1 over 1 minus negative x over 3. So discounting the third and just looking at what's inside the bracket, these two are identical. Except these two are identical. So except for x now being negative x over 3, they're exactly the same. So I could just apply this formula. And so I get 1/3 times the sum of n equals 0 to infinity. But I don't have x to the n. I have negative x over 3 to the n. Awesome. And of course, if you need a restriction, think of it like this. Instead of x, it's negative x over 3. And this needs to be less than 1. And so x is less than 3. Great. So there we go. We found a power series representation for 1 over 3 plus x. Right? 1 over 3 plus x is equal to this, as long as x is between -3 and 3. So let's see what happens as we integrate. So let me integrate this. And the whole point of why I want to integrate this is so that if I integrate this function, then I get back ln of 3 plus x. That's how derivatives and integrals work, right? Taking the derivative is kind of like taking the opposite, opposite of integration, right? Integral, if you take the integral and then the derivative, you get back roughly the same function. The only thing you might have to worry about is plus c's. So, integral of 1 over 3 plus x dx is equal to the integral of, come on board, let's go, integral of 1 over 3 infinity negative x over 3 to the n. And this is dx, because I'm integrating with respect to x. All right. So this, on this side, I know is ln of 3 plus x. Right? And you might say, Alex, where's the plus c? I'll add it on the other side when we get there. So this is equal to 1 over 3, because I can factor the constant out. I'm just going to scroll down a little bit so I have more room. 1 over 3. And because the sum here, the variable is n, I can actually move this integral in because I'm integrating with respect to x. So n equals 0 to infinity, integral of negative x over 3 to the n dx. And remember, when we take the sum, it's the sum of this whole thing here. So this is ln of 3 plus x is equal to 1/3. And now the issue is, I don't really know how to integrate negative x over 3 to the n. It kind of looks like a polynomial, and well, it is. But the negative thing is throwing me off. So this is actually equal to n equals 0 to infinity, the integral of, well, actually, hang on, why don't I do this? So I can say this thing here, this is equal to negative 1 to the n, x to the n. Right, so I'm just splitting this up over 3 to the n. So because I'm integrating this, you can think the only thing that really depends on x is the x to the n here. So everything else I can factor out. So negative 1 to the n, 3 to the n, integral of x to the n dx. So everything else I factored out, so I'm just taking the integral of x to the n dx. Well, that shouldn't be too hard. This is just power rule. And so, ln of 3 plus x is equal to 1/3 times the sum of n equals 0 to infinity, and I'm just going to write this quickly, times xn plus 1 over n plus 1, and if I collect all of the constants, I can just say 1 big plus c. Right? When you take the integral, it's plus 1 on the top, because it's power rule, plus 1 on the top, divided by the new exponent, n plus 1. So here you have it. Here is a power series representation for ln of 3 plus x. So that's great. Before, we had that this converged for x, the absolute value of x less than 3. So this may still be the case. Again, if you saw my previous video, you have to kind of see what happens at the endpoints. If you integrate or differentiate, just make sure the same things happen at the endpoints, right? I mean, you still have to go back and check whether it converges or not. So, first of all, actually, we should probably get rid of the c. So, if x is hang on a sec. Hang on a sec. Sorry about that. All right, okay, back to this question. So what happens if I take ln of 3 plus x is equal to this thing, and I'm trying to look for c? Well, a convenient value to pick would be x is 0. If I pick x is 0, this whole thing disappears. So I can just choose x is 0. Right? If I choose x equals 0, I've got 0 to the power of, the first number I would have is 0 to the power of 1, because I choose n equals 0. So this whole thing would actually disappear and go to 0. So c is equal to ln 3. Right? This whole thing is 0. C is equal to, I plug in 0, ln 3. So that would be my power series representation for ln of 3 plus x. So ln of 3 plus x is simply equal to 1/3 this over 3 to the n, x to the n plus 1 over n plus 1, then plus ln 3. And this is valid for x between -3 and 3. All right, so let's just recap what we did. We have ln of 3 plus x. We know that the derivative of ln of 3 plus x is equal to 1 over 3 plus x. And this one, I'm pointing at the screen, of course you can't see, but 1 over 3 plus x looks a lot like 1 over 1 minus x. And in fact, we can manipulate it so that we can make use of this formula, right? So I've factored out the 3. If there's something on the top, you could just leave that on the outside for the time being and then multiply back in afterwards, just like in the first iClicker question we did last Friday. So this, I can use the formula and actually get back this. So that's all fine and dandy. So it's 1 over 3 plus x is equal to this power series. Well, if I integrate 1 over 3 plus x, I know I get back ln of 3 plus x, which is what we're looking for in the first place. So I do exactly that. I integrate both sides, and I get this. And perhaps the trickiest part is knowing that you can move the integral inside the sum, and then you pull out the parts that aren't relevant to x, right? -1 to the n will just be a constant, 3 to the n will just be a constant, and you can factor these things out. And so you're just left with x to the n dx, right? And of course, according to power rule, it's x to the n plus 1 over n plus 1. And we know we can do this for power rule as long as n is not -1, right? And n is not -1. So that's all good. We integrate both sides. And in class and in my slides, I put an emphasis on taking a look at integrating each term if I break it up. So that's perfectly fine too. You can do it that way. But I find that if you leave it in the summation form, then you don't kind of have to recollect and try to figure out what it looks like afterwards, which is a little bit nicer. So anyway, you integrate. Don't forget the plus c. There's a plus c. And then you choose a convenient value of x, which in this case is 0, to solve for what c should be, right? And we found that c was ln 3. And there we have it. That is your power series representation of ln of 3 plus x, right? You just find a derivative or an integral that looks a lot like 1 over 1 minus x, and then you do something with it to make it look like 1 over 1 minus x. Then you do the opposite process to get back to your original function, right? So beforehand, we took the derivative, right? We took the derivative to get to 1 over 3 plus x. So we had to integrate the power series to get back to the original function. So we had to integrate to get back. So that's the whole idea. Of course, here, I guess I could have thrown the 3 back in and be 3 to the n plus 1, but both are perfectly valid. Anyway, hopefully that helps and is a good example for you to understand what's going on here. Thanks for watching.